Okay, guys, we're going round 2 in Quaternions. We're going to figure these things out, so I got this other video. It's Fantastic Quaternions by Numberphile. Yeah, let's get into it. I'm super excited. I'm looking forward to this, so let's get into it.
3 dimensions. So you take an object like that and rotate it.
Sorry, I usually watch stuff on 2 times speed. Let's go down. Boom.
How do you rotate an object in 3 dimensions? So you take an object like that and you rotate it. That would be something that's useful, you can imagine, in computer graphics. But how are you going to do this? Now, one of the neatest ways of doing this mathematically uses a new type of number beyond the regular numbers you know. So there's beyond the real numbers, as we call them. They're even beyond the complex numbers. If you've heard of complex numbers before.
Also, sorry if I'm not making as many jokes in this video. It's kind of like late, so I don't want to wake anybody up. So
even beyond that, they're called Quaternions. They're fantastic. So imagine I want to move along in 1 dimension. So you're living somewhere here. And if I said move +5. +5 means you move 5 units to the right along this line. So I'd end up over here. If I said instead move -3, you might understand that means move 3 units, but that time move 3 units to the left. So that's how you move in 1 dimension. That's fairly easy, isn't it? All right, let's talk about moving around in 2 dimensions. And let's say I want to end up at a point over here. What that might be, 3 units this way, let's call that a 3. And then I move 4 units up, like that. One way you could write that as a set of instructions is to write it as 3 + 4i. Some of you may know what's coming here. Some of you may have seen this I before. But for now, let's just say I means turn 90 degrees and go up and down. Right, for now, that's what it means. All right?
okay, that makes more sense. I've never really gone over complex numbers like that yet. So yeah, I understand. So I is just like going up the vertical axis. Okay.
So that's one way I could travel to that point. Or alternatively, I could look at it this way. I could travel 3 across and 4 up. Or I could rotate myself to this angle here and move along this diagonal line here. And that would be 3 + 4i as well. Right? You could use the same instructions to make that point. That's how you travel in 2 dimensions. I mean, if I want to then go further and travel maybe a bit further on. So let's say I wanted to go maybe 1 more across and then 2 up, like that. What I could do then, by adding a further 1 + 2i, I end up at this point. And I can say that this point is the combined result, which means I've actually travelled, what, 3 across and then a further 1, 4 across and 6 up. Or, if you like, it's the combined result of going from here up to here. So we can add these numbers together, and we should think of them as numbers. Right? You can add them together, and you can move around in 2 dimensions. So this time, let's rotate this line. Let's take my combined result here. What have I got? This is 4 + 6i. Let's rotate this 90 degrees. If I rotate it 90 degrees, I think it's going to end up something like that. And it will end up here. It will end up on a point here. So this is going to be a 90-degree rotation. This point is actually -6 + 4i. And that's where I end up if I rotate. These look similar to each other. Why do they look similar? How can I get from this number to this number? What I've done actually is I've multiplied. Instead of adding the numbers together, I've actually multiplied this time by the number, we call it a number, the number I. So there is a special rule with this. The special rule is I times itself, I times I, is equal to -1. Just to show you what I did, I took where I was, 4 + 6i, I multiplied it by I, and what did I get? I got 4i + 6, well, let's call it I squared. Oh, what is that? That is 4i - 6, yeah. Or in other words, where I ended up here, -6 + 4i. So multiplying by that number I means you rotate 90 degrees. If you do it,
that's just such crucial information. You know what I'm saying? Like, I feel like in those other tutorials that would have been so helpful to know. But anyway, we'll continue.
Twice you get -1, which does make sense. So if you rotate 90 degrees and then rotate 90 degrees again, You're 180 degrees now, you're facing the opposite direction, so you're going negative direction, so it does make sense. And it turns out that if you multiply these numbers together, you get rotations. When you multiply the two numbers together, you add their angles together. So if I want to rotate 45 degrees, I'll get my triangle for 45 degrees. 1 over root 2 there, 1 over root 2 here. Oh, so that's nice, and that's a 1 now. That is a 45-degree angle. Written as a number, that is 1 over root 2 plus 1 over root 2, lots of I.
Oh my gosh. Wait, that's crazy. Okay, that makes sense. Okay, all right.
There you go. So I've gone that distance across and then that distance up. If I multiply by that number, I would rotate by 45 degrees. So adding them together makes you travel around in 2 dimensions. Multiplying them together makes you rotate in 2 dimensions. Now, if you're ahead of me and if you've seen this sort of thing before, you may recognize these as complex numbers, which, by the way, is a terrible name. Complex numbers, which makes them sound like difficult numbers, which I don't think is the intention. I think the idea is they are compound numbers. They are actually 2-dimensional numbers. That's a way of thinking of.
Who is this guy? I'm so curious to know. Dr. James Grime. Dude, this guy, I'm so curious because he just like made math, right? Not like made math, but like he just renamed. He's like, yeah, actually, like complex numbers is a stupid name. I'd just probably call them like compound numbers. That just definitely seems like someone who's correct. Public speaker, mathematician. What other stuff has he done? This is just the AI report. I don't know why I'm looking at that. He just seems like a G, honestly. I don't know why. He's just a mathematician guy. Well, he looks like he knows what he's talking about.
Complex numbers. Real numbers are 1-dimensional numbers. Complex numbers are 2-dimensional numbers.
2-dimensional.
And you can use them to travel in 2D and rotate in 2D. So the question is, how do we rotate in 3D? We must need 3-dimensional numbers, right? So we must have to introduce an I and a J as well. So we have 3-dimensional numbers, and that's what people thought. It turns out we don't need 3-dimensional numbers. We need 4-dimensional numbers.
Wow, he really tickled me right there. Just like you had it on a string, and it's like, wow, got me at the edge of my seat.
To rotate in 3 dimensions, bizarrely, you need a 4-dimensional number. Let me show you how this works. So right. So there was an Irish
That's what I do, like 90% of the time, except they cut it out. Maybe I'll just keep it in this
mathematician called William Hamilton, and he was thinking about this problem, and he couldn't solve it. He said, it doesn't work in 3 dimensions. I can't get it to work. And the story goes that he was having a walk with his wife along the canal in Dublin, and then suddenly inspiration struck, and he realised, I don't need 3 dimensions. I need 4-dimensional numbers. I need I, J, and K. So flushed with this, he immediately...
I hope that one day I'm on like a walk with my wife and I'm just like, oh my gosh, you don't need 3... I don't even know what to say. Just something crazy. I wish I came up with a cooler joke. Maybe that's my moment right there. I was gonna come up with something sick. It didn't happen.
He walked over to a nearby bridge over the canal and he carved in the rules that he needed to make this work. These are the rules that he carved into that bridge. I squared is equal to the j squared, which is equal to the k squared, which is equal to I times j times k, which is equal to -1. It's very similar to the complex number idea. The complex numbers, I squared equals -1. That's what we needed for that. It's very similar, but no, we need I, J, and K. He carved this into the canal bridge, which unfortunately, graffiti, what a vandal. Unfortunately, it's not there anymore, but now there is a plaque celebrating the rules, or his discovery of Quaternions. The rules are there, And
wow, what a bunch of nerds, literally. Community of nerds right here. It's actually kind of sick. I'd love to carve something and then they write it about me, like on a plaque.
every year, mathematicians around Dublin have a pilgrimage to the spot where he had this idea for quaternions for the first time. So by multiplying these four-dimensional numbers, you can now rotate, like the 2D version, you can rotate things in 3 dimensions, and this is how things are done using computer graphics. But not only that, it's how things are worked out for the rotation or the orientation of a space shuttle going up, or it's how they work out the orientation or the rotation
I thought he was gonna like pull out a gun or something.
of your smartphone. So let's say I want to rotate an object in 3 dimensions. What I do is I pick a line like this pen here. I stab the object with this pen, and then I can rotate around this pen here.
Yeah, you're just gonna take your pen and you're just gonna stab Bill in the corner. You just stab him with the pen, and then you're just gonna rotate him around.
So I might stab it this way, and then I can rotate the object like that, or I might stab this way, so it rotates the object this way, or else this way, and so we can rotate like that. So how do we write this? So I take a line like that, and then I want to rotate around that line. Let's do it.
Oh my gosh, that's what was in the last video. You stab it in, and then you do the rotation, and then you do the Q hat, the conjugate. I remember that word. And then that's what allows you to isolate the angle and overload.
Do an angle of theta like that. Let's call it V. This line we're calling V. Call that a P, and that's sort of X, Y, and Z for that point in 3 dimensions. This is how things work. But now we're going to rotate it using a quaternion. What does a quaternion look like? It looks like this. A quaternion, let's call it H, would be something like A plus BI plus CJ plus DK. And actually,
DK, my main.
for this, I do need
Just kidding, I don't mean DK.
another
I kind of suck, so.
little thing, something called H star. And H star is A minus BI minus CJ.
Fun fact, that word's called the negation. If you watched the last video, understood, I couldn't understand it
Minus
for the life of me.
DK. Right. If I want to rotate by an angle of theta, A, B, and C are defined as A is going to be equal to cos of theta over 2. B is going to be written as V1, that's come from my vector here, that my stabbing pen, sine of theta over 2. The C is V2, lots of sine theta over 2. And the D needs V3, lots of sine theta over 2. So it turns out we need 4 components for our number that we're going to use. We need 4 components to have the freedom to do the stabbing and then the rotating around that vector.
You're also going to need some illegal weapons. Actually, you don't need illegal weapons to stab. What am I talking? That was so dumb. That was such a dumb thing to say. I could do that with like... I'm just going to shut up now.
And how do you work out the rotation?
Guys, it's so late. My humor is just... It's just not even there. I feel so bad.
Finally, if P, which is the point I'm rotating, you write P as a quaternion. Its coordinates are x, y, and z. It's actually x, lots of I, plus y, lots of j, plus z, lots of k. And finally, the rotation is h, p, h star. Right, that's the maths of it, right? That's the main maths.
Wait, I feel like I'm here. I'm kind of here. So, P is the point. Okay, so we're taking the point, and then H is the quaternion, so we multiply. Okay, so what we're doing is we're taking the quaternion, and then, we skipped that. So we're taking the quaternion, we're applying it to H, or the P, the point. It's gonna rotate it back. Do the, I don't even know what I'm saying.
And how do you work out the rotation? And then finally, if P, which is the point I'm rotating, you write P as a quaternion. its coordinates are x, y, and z. It's actually x lots of I plus y lots of j plus z lots of k. And finally, the rotation is h, p, h star. Right, that's the maths of it.
I was watching this other resource that's basically saying like a quaternion is taking like the rotated space, bringing it back to normal space, doing the adjustment, and then rotating it back. So that's how you translate in like a rotation. I don't think this is what I'm talking about, but I feel like
Of
it's
it,
connected.
right? That's the main maths. But we need 4 components to our number to have the freedom to be able to rotate around a vector and then move the angle around it. So the complex numbers contain the real numbers as well. And it turns out the quaternions contain the complex numbers, and in turn, they contain the real numbers. And when you don't need the j and the k, now you've got a complex number, and if you don't need the I, you've got a real number. So you might be thinking, what's next? Is there a next step up? And there is. The next step up is octonions, 8-dimensional numbers.
I'm not fetching ready for that yet, please. Please.
Octonions, which have
What's your name again?
their own
Please,
set of
James,
rules,
have mercy
as
on
well, very similar, but a very similar idea. But every time we go a step further, they get a bit more abstract. They lose a bit of structure, and there's a property that you lose each time you do it. So the more you do this, the less useful.
This is piquing my interest. What is this? Extra footage? Oh, there's so much. All right, let's finish
They
this.
become. Octonions have some uses in very abstract maths, but they're not as useful as quaternions are. And there is then a step above that. The 16-dimensional numbers, the Sedenions.
Please.
But again, you lose
so
another property when you go further. And each time you do, they get perhaps less useful.
All right, I'm going to be honest. I feel like I'm getting closer. I'm getting closer by the second. But this part here, okay, here's what I don't get where he got this stuff yet. I get this is what a quaternion is. This is the negation, or this is negation. I kind of get why you multiply that by the point that we're trying to solve for the rotation after rotating. So that's kind of where I'm at, and I think that's just like that's the bridge I need to kind of connect. But I think I'm gonna end this one here. Gonna sit on it for a bit, and then hopefully by the next one we'll have it down. Oh yeah.